MAVEN is a spacecraft at Mars that's part of the Mars Scout program. MAVEN's primary objective is to understand the evolution of the upper atmosphere of Mars. We know that liquid water once existed on Mars, oceans and lakes and rivers of water. But where that water went has been a mystery. For water to exist in stable liquid form, you need to have enough atmospheric pressure. So what happened early on in Mars's history is the atmosphere started getting eroded away, namely by processes and drivers from the sun. That atmospheric pressure got lighter and lighter, and then the water started evaporating, and some of it was trapped in the surface, and then a lot of it escaped to space. There are many ways that the atmosphere can escape, but the one I've been focusing on for the last 10 years is called sputtering. Sputtering is like doing a cannonball in a pool. The cannonball would be the heavy ions coming in really fast into the atmosphere. And as they hit the atmosphere, they splash particles out. When MAVEN first arrived at Mars, we thought we would see sputtering immediately. But it's an exceptionally elusive escape process to observe. We've had hints that this process exists and is operating at Mars through things like isotope ratios. Argon has different isotopes. Some of them are lighter and some of them are heavier. What MAVEN found was that the lighter isotopes are preferentially removed in the atmosphere. This is incredibly hard to do, and no other atmospheric escape process could explain a ratio like this. Think of it like stumbling upon ashes in a fire pit the morning after a campfire. Now, you haven't actually seen the fire yet, but you're pretty sure it existed. In 2017, MAVEN found something like this, the ashes being isotope ratios. These isotope ratios gave us a hint that sputtering must exist. So in this result, sputtering is the fire. What we saw was argon at high altitudes correlated with the electric fields driven by the solar wind. We had to have observations from 3 instruments simultaneously. We needed to measure the solar wind from SWIA, we needed to measure the magnetic fields from our magnetometer, and then we needed to measure argon with NGIMS. It took 10 years of data to finally find the statistics and have enough data from each of those 3 instruments to be able to put this result together.